Okay. Yeah. So welcome. Yeah. So welcome. As I was just saying, just while we're getting started here, we will eventually go back and play around in Excel, and we'll use the same or similar file as we did last Friday. And there's just a slight tweak, so it's okay if you just use the same one from Friday, or I've re-uploaded it. It still is called Regression Friday, even though this is Wednesday, but it's on Canvas. So if you want to pull that up and watch or play around with it as you're watching this video, or watching me live, feel free. Otherwise, it's there for your future use. So, yeah. Um, let's see. So today, this is our last kind of get together, last lecture before your reading week, and that yeah. So then you have the whatever it is week or so that brings us to the exams for this class are scheduled for December 8th and 9th, depending on which section you're in. We'll do a similar format as the previous exam, so actually you'll have it kind of both of those days. So you'll have it available on December 8th and 9th. So that means whatever the defined time that you are scheduled for the exam, the final exam period, you will have the exam available. So shouldn't be hard finding a window of time to work on it. And yeah, so just other things to note. So I will keep my current office hours, and I'll probably expand those a little bit and maybe add in another day through this kind of reading week. So if you have questions or want to chat about what you're studying or statistics in general, please make use of those. Yeah, so today, what's our goal? We want to be introduced to some more ideas around regression. Now, as I said last week, we're not going to become masters of regression here in a week and a half. Regression can be a full semester long course. There's a lot of nuance to it. But we are getting exposed to kind of the core concept and the core methodology. In some sense, maybe to put it in context, back in chapter 11 specifically, we dealt with these kind of very nuanced questions about, do we know that the population standard deviation is the same, or do we not? That little question, right, led us on kind of a different path in the decision tree as far as which T statistic do we exactly use. Broadly speaking, there's a lot of those kind of branches in regression. So there's various questions you kind of have to answer as you decide what specific method of regression do you want to use. So that I point that out to say that as you dig deeper into statistics, or as you see this in play, there's a lot of little deviations from kind of the core that we're learning, but it's all based around the same concept. And so hopefully this introduction to this will give you kind of a framework to build on and to understand. So even if you don't take further statistics courses, hopefully you'll at least be able to understand what the point of regression is and why it's used and what it's attempting to do. Yeah, and I would say, so remember we're using what's called ordinary least squares, OLS, and it is it's pretty close to all these other types of regression, but it's also very easy to interpret. And so actually, think about all of those decisions you have to make as to which regression you're going to run. Typically, people make those decisions, run a certain regression, but they also run this basic structure of an OLS and report those results as well. So this version that we're learning is heavily used and widely reported for those reasons. Okay, so Yeah, so let's ramp back up to speed. So what have we been tackling here in 13 and now 14? So we've been dealing with correlation at the heart of it, right? So we first learned how to calculate correlation based off of that kind of same idea of deviations from the mean, but now in 2 dimensions, right? So we're talking about x and y. And so we're not squaring the deviations in x, we are multiplying the deviation in x and the deviation in y. And correlation is giving us that linear relationship between these variables, right? And so we were able to pick up linear relationships between 2 variables. Now what I want to drive home today, just briefly, is that we do need to be mindful that we are talking about linear, okay? And so we've been dealing with, we can pick up that there are these linear relationships. These are moving together, either positive or going the other way and going negative. But I'm going to briefly just pull up a few websites here if I can find the right. Yeah. So let me. Yeah. Okay. So we'll try to click these things in the right order so I'm less harsh on my computer so we don't drop it again. But so this data or this website is going to kind of real time calculate the correlation for me. So what I want you to focus on mainly is this Pearson correlation, which is one method of calculating correlation. And we can see, so as I click in here, so the moment I put 2 dots down, right, 2 dots are always going to produce a correlation of 1, right? Because we can draw that perfect line that goes in between both of them. Should be able to clear. Okay. So no matter where I draw them, it's going to be a correlation of 1. We can also, remember this was a really tight correlation, 0.997, and it's not based on the slope. So when I do something like this, oh, I hit it right on. Pretty good. We can also get a very high correlation on both slopes. But what I want to highlight is that this is a linear relationship. Okay, so if I draw something like this, notice I have a very small correlation. So there's a slight positive correlation here, but that correlation is a straight line that slopes kind of through the middle here, right? So it does not indicate any type of this bend to it. So correlation is only picking up that linear relationship. Now, so this brings up the idea that oftentimes we calculate the correlation, but when we're dealing with data, when we're analyzing data, we often also plot a scatter plot because we can miss some of these types of relationships if we only look at correlations. And these types of relationships exist in the wild, right? So if you were to plot happiness, for instance, on the y-axis, so if you're trying to measure, maybe you're interested in what makes people happy. Is it income, right? You might have, those studies came out a number of years ago about what level of income, starts to peter off and you don't get more happiness. And I think they found as long as you're making 75,000 or something, it doesn't matter if you make more. Anyway, that's beside the point. The point here is that if you plot age on the x-axis, so if you have happiness and age, you will get something somewhat like this. Okay, and that to scare you off, the low point in happiness for age is somewhere, I think it's in the 40s. So what is that saying? That's saying things are going to get worse. This is not a happy thing to say to you, but typically we see a relationship between the 2 variables, but it's not linear. Okay, so we can't pick that up with a simple correlation. Now, to put your mind at ease, of course, this is not a 1-to-1. So you can have people that are happier in middle age. Okay, so this could be you up here. So you're not stuck with what the data says. Okay, so that can be a close to 0 correlation, even there's a relationship. We can also have, another thing that shows up is some type of a cyclical relationship. Again, this can show a pretty small relationship or linear relationship. I do have, I guess, 0.4, maybe if I bring that down. Anyway, we can show not a very strong correlation, but clearly there's something happening here. And so we might see something like this with what I said, cyclical. So maybe things that change by day of the week or quarter of the year. Maybe this is each a new quarter. So a lot of financial data comes out quarterly. And sometimes depending on, maybe the first quarter of every year is higher compared to the others. So again, we don't always pick up everything based on simple correlations. We can even have, we could have something like this that has a strong negative correlation. But if there's something else happening where we have another chunk of data, okay, so maybe some people are in this range and then some people are up here. And notice we have two parts that have what we would say is a negative correlation, but because we've plotted them all together, we have actually a positive correlation. Okay, so just some things to keep in the back of your mind, that just looking at a correlation doesn't always tell the full story. Okay, so, and we can take that to the extreme, and I'm going to show you a picture of somebody drew this. Actually, I think I'm gonna credit Alberto Cairo on this, but I think that's who first drew this. But this, if I was good enough to draw that in that same program, gives a correlation of 0. Okay, so again, obviously a relationship, this time purposely to be a T-Rex, but this produces a correlation of 0. And in fact, here we have a series of relationships that are all correlation of 0 or really close to 0, but clearly there's some connection. So that's all to say that correlation is not the end of the story. Now, I don't want to poo-poo correlation too much. It's a very useful and powerful tool, but it is all about linear relationships. Okay. So we moved from correlation, or we used correlation in our calculations for regression. And our first entry to regression, we talked about fitting a best line through our data, right? And we had data that looked something, I don't know, something like that. For our milk and kids, and we talked about fitting a best line in here. This isn't exactly what we had, but remember, it's always going to go through that middle, or that mean point. This is not exactly what we had, but we had something similar. We talked about fitting that best line through the data, and it's best. What do we define as the best? Well, we have to choose what we think that metric's going to be. And the one that we're using is that least squares. So that's where the ordinary least squares comes from. We're talking about the least squares. And really what we're saying is that we're going to minimize the sum of squared residuals. And to refresh, the residuals, we can think of it as a deviation, right? So just like in standard deviation, correlation, we've been talking about deviations. This time, we're not deviating from the mean. We're deviating from the line. Okay, so we're going to be measuring how far do we deviate from where this line is. So each of our data points, in this case, we just have the 4 red data points. Each of our data points, none of them fall directly on the line. So each one has a deviation from that line, or what we call a residual. The residual being the distance between y and y hat, okay, and where y is each data point, and y hat, this is going to be too many lines, but y hat is the line, and we say y hat as one way to think about it is the predicted value of y. Okay, and we'll talk in a few minutes here why I say prediction. That's one of the reasons we use regression. So in some sense, our line is predicting where we think y is going to be. And we're not going to hit it. We're often not going to hit it right on. We're not going to hit it right on, and so there's going to be a deviation. And that's the deviation, or the squared deviations, the squared residuals, that we're trying to minimize. We're minimizing the sum of all these squared residuals. So we can think of y minus y hat as the residual. And again, we're not minimizing the residuals, the sum of residuals. We're minimizing the sum of the squared residuals. Okay, and that's a decision we have to make. And again, some of those variations in regression change what our definition of best fit is. So you can run a form of regression that minimizes the sum of residuals, or the absolute value of residuals, right? Just like we talked about, sorry, my hair is out of control. We talked about that in standard deviation, that there's variations on that to say, maybe we don't want to take the squared deviations for standard deviation. Maybe we want to run something like absolute value deviations. We can do a similar thing here, and that's some of those differences in types of regression. But the standard one, the OLS, we minimize the sum of those squared residuals. So, but our overall goal here is to get the equation for this line. Okay, so we want to find the equation y hat is equal to a plus bx. Okay, and that's going to be the line that best, as we've chosen it, best depicts this data. One of the reasons we do this, so there's a few reasons to regress or to use regression. One of them is to predict. Okay, so if we think about our kids and milk example, we may want to predict how many gallons of milk a family might want. Why would we want that? So maybe you run a food pantry and you are trying to give the right amount of milk to a family that comes in. And you have a family walk in that has 9 kids. You could guess the average amount. Okay, what did we say? Average was something like 4 gallons of milk. But this family has more than average kids, and so maybe you want to guess higher than the average for gallons of milk. And this would be a way to do it. You would find what value is along the line at 9 kids, and look over and say, okay, this is 6 gallons of milk. Okay, so that's one of the reasons we use regression, is to better predict what we think y might be for a certain x. And once we have this equation, we can simply plug in x. So how do we find this? Well, we're gonna learn a method of doing this for simple regression. Now, this is not necessarily how Excel does it in the background, but this is useful to kind of understand the relationship between correlation and our values. So the process that you're going to have to plug through on the homework, if you haven't done that yet, is we can find our correlation, right? So let's say we know the correlation between these two variables, right? That's R. We can take R. If we multiply it by sy over sx, that's actually b. Okay, so in some sense, remember correlation is independent of units. Here we're putting the units back in, and we're saying the relationship in these units is b. Okay, so as x changes, y changes by b amount. Once we have, so kind of the process is find correlation, use that correlation to calculate b, and then use b to find a. Now again, we talked about this the other day, but how do we do that? Well, we use the formula, or we use the equation. Let me just get out of the way for a brief moment. We use the idea that this line is going to go through the mean. Okay, and so we can solve for a and say a is equal to y bar minus bx bar. Okay, and if we know b and we know the mean, we can just solve for a. Okay, so that's the flow that we'll go through to quickly solve for this regression. Okay, so loosely speaking, that would lead us, maybe I'm just going to make up these numbers, but maybe we've solved for a and b, and we know that y is equal to I had one written down, but we'll just make it up. Okay, so 2 plus 3x. Okay, so maybe we found that a was 2 and b was 3. So we now know this line, and we could say, all right, I think, or I know an x is going to be 4. Okay, this is not the milk, and this is not the exact numbers from the milk in kids, but let's say it's some other, kids in boxes of cereal. Okay, and we know that there's a family with 4 kids, and so we can plug 4 in for x and find that y hat is 2 plus 3 times 4, so 14. Okay, that seems a lot, but that's what our prediction would be. Okay. Yeah. So, so that's kind of where we were. The other thing I just want to point out, and this doesn't quite flow in this discussion, but I do want to point out that this R in your homework and when we're dealing with regression, we often are asked about R squared. Okay, and R squared, and actually oftentimes it's written with a capital R. R squared is simply R times R. Okay, so when you need to do that, when you need to calculate it, it's just correlation times correlation. It's, if you find a R of 0.7, then R squared is 0.49. Okay, it's 0.7 times 0.7. And so just to rehash that, so you're ready to do that calculation, and R squared tells a certain information, and one way it's interpreted is it's telling us how good our prediction is, okay, or how well we can predict y based on x. Another way to say that is R squared is the percent of variation in y. Okay, so y is moving around a lot. There's a lot of, maybe not a lot, maybe there's a little variation, okay, but how much variation is there in y? So as we move through the data points, y is moving up and down. How much of that can be explained by where x is and where x is moving around, how much variation there is in x. Okay, so it's the percent of variation in y that can be explained by the variation in x. And so it's often interpreted as kind of the strength of your prediction of y. Okay, so I just thought it was worthwhile to rehash that again. So we're going to turn to Excel now, and again, if you're just picking up midway through this is that same, it's Regression Friday on Canvas. Let's do that. Okay. And so it's the same one as last week with just a slight variation. So if it looks a little different, you can re-download the file, or just I'll point out the one change that I've made. So we walked through a bunch of this the other day. Let me zoom in a little bit. Yeah, we saw how to kind of do correlation by hand on Excel, but then we also saw that Excel can spit out correlations that look kind of like this, and we can get it directly from the data analysis toolpack. And we also saw Excel put out a regression, and we can do that. Let me just walk through it. So data analysis regression, we want to grab the y. Okay, so you do want to make sure you put the y as the one you want. You can flip that around. It's just going to give you different coefficients. You're calculating a different equation there. Okay, so I do want labels. I'm actually going to keep residuals on this time. Oftentimes we don't plot or put the residuals out there, but I'm going to have it show those, and then we just pick a spot to put that. I'm actually going to, when I click OK, it'll spit out most of this. So I'm not actually going to do it because I want to just keep the highlighting that I have. But you would see this. Okay, now when we run a regression, typically our eyes jump down to this area. Okay, I highlighted it. It doesn't come highlighted, but this is a lot of the information that we are interested in. We also get the correlation and the R squared. Okay, so this is correlation. This is what we calculated up above, the 0.8366. We can zoom back up. That's this correlation and the one up here. Okay, so if you run a regression, you get the correlation as well. at least in this simple version. Okay, so R squared is simply this correlation times correlation. Oh, that's not what I wanted to do. And there we have it. Okay, so this is 0.8366 squared. But, okay, let's focus in on where we typically do. We have this information for us. Okay, so we get the coefficients. So the coefficients are A and B for us. Okay, so this is spitting out A and B. So we get A as negative 0.9 and B as 0.7. Let me pull this up real quick. And hopefully not kill my computer. Okay, so remember we're oops, let's come down here. So we're trying to measure again y hat as a plus bx, right? And so what we found is that y hat is negative 0.9 plus 0.7x. That's very poorly drawn. Negative 0.9 there. And that's what this regression is spit out. And in fact, if we go back up, this would match what we've found with the right. So here is Excel doing it for us in that scatter plot, adding the trend line and showing the equation. And in fact, we see that it's reversed, but it's 0.7x minus 0.9. And so we get the same result. And here's that R squared. How well does this predict y based on the x's? That's at 0.7, which we also saw down below. Okay, so so what else are we getting here? So Excel is also calculating the standard error and using that to do a t-test. Okay, so as we see in chapter 13, and this is true in 14 as well, is that we can test whether or not these coefficients are different than 0. So we are running a t-test, much in the same idea of, remember so same process. We're running a t-test, we're testing the hypothesis of, is B equal to 0, where the alternative is B is not equal to 0. Okay, and B equal to 0 would mean there's no relationship between in this case, kids and milk. Okay, so we're running that test, and Excel is going to do that for us. And so that test, remember, is going to be B minus 0 divided by the standard deviation of B. Okay, that's kind of hard to see, I realize. But that's, the same flow as chapters 10 and 11, a distance up top and that standard deviation. In this, we just call it the standard error on the bottom. How much is that moving around? So we run a t-test. Excel is going to do that for us. So one thing to point out is that we really don't care about the intercept. It doesn't tell us anything. I mean, we need it for our equation, but we don't focus in on the t-stat or the p-value for the intercept. We do often take a look at those for the B. This is a t-stat of 2.16, but remember, so that's a pretty big t-stat, but remember we have what? We have 4 observations, so our degrees of freedom is 3. So if you recall from the t table, the critical values get very large very quickly at that low. So we don't actually find, we didn't set up an alpha, but any reasonable alpha of 0.1, 0.05, 0.01, we wouldn't have found this in the rejection region. Okay, so the p-value of 0.16 tells us that unless we had chosen, a obscure, 0.3 for our alpha or something, we're not going to find it in the rejection region. But of course, that's largely driven by the fact that we only have 4 data points. So we wouldn't, even if we found a p-value of below 0.05, we probably wouldn't want to take a lot of stock in a 4 observation situation. But the process here, I just want to highlight that we're getting that information on Excel. Okay, so what can we do with this? Again, let's talk about trying to use this to predict. And I think maybe I'll just clear this off. So again, we're trying to build, actually. Remember, we're getting this equation, y hat equals a plus bx. And in our case, that's really milk hat. Okay, so milk hat, we could write it out as milk hat equals a plus b kids. Okay, that would be, sorry, that's really hard to read, but and so let's actually build that. So we're gonna write that out. So milk hat is equal to what? It's equal to a, which is, where can we draw that from? The intercept. Okay, so it's equal to a plus b times kids. And now I'm gonna click in here. There's nothing in there yet, so that's gonna treat it as 0. But now what I have is a way to quickly predict how many gallons of milk we might need for a certain sized family. Okay, so if I plug in 5 kids, we say our best prediction, or a better prediction, is 2.6, right? Again, we could always just predict that each family needs, what was our average? 4 gallons of milk. But because we see there's a relationship here, or we can use this relationship between kids and gallons of milk, that we can perhaps get a better guess. So, yeah, so what did we just found? We found that our prediction for a family of 5 kids is 2.6 gallons. Let's go back up to the scatter plot. 5 kids is right in here. I don't know if you can see my mouse very well, but we have 5 kids here, and that is 2.6. If we that's what that would be if we scroll over. Okay, so what we're picking up is, where is that line when we have an x of 5? The y value is 2.6. Okay, so that's all we're doing when we're predicting based off of this. Okay, and we can quickly plug in different values. Okay, and what did we say before? We talked about that family of 9 kids. We might want to say 5.4 gallons. Again, that's up here somewhere, right? So one other thing, I had Excel, sorry to scroll around so much. I'm just going to bring our data down just so we can look at it a little closer. We had Excel output the residuals, and I just want to show again what that is. So we had a family of 4 kids. Our predicted value for a family of 4 is not exactly what that data point was, right? So just our predicted value for 4 kids is a little less than 2, and we did have a family, and they only needed 1. So when we think about the residual, we missed by what? We missed by 0.9, right? So again, if I plug in 4 kids, we get a prediction of 1.9. We are off by 0.9. Similarly, when we have a predicted family, or when we have a family of 6, it predicts that we need 3.3. This family needed 5, and so we're off by 1.7. Right? So again, that's that distance between the data point here and the line, the residual. And we do that for the following 2, right? We can plug in 8, calculate that distance, and same with 10. And so now we have the residual for all 4 of them. So what this line is, so if I square all of these, okay, I've squared this residual. I'm going to do that for all 4 residuals. And then I'm going to sum these up. Okay, and this is not going to be 0. It's not going to be, it's 4.2. What do we know about 4.2? Well, this is the smallest sum that we could have possibly gotten. Any other line, any other coefficients here, if we change this to 0.6, and this to, 1.2, negative 1.2, any other combination of coefficients, the squared residuals is going to be larger. Okay, 4.2 is as small as we can get that. And that's what this process does. It minimizes this value, this sum of squared residuals. Okay. Yeah. Okay, so let's talk a little bit about how we interpret this. So I do want to point out, and we'll talk about this more later, that we're not making a causal statement necessarily. Now, we might feel comfortable talking a little bit of causal, like you add more kids to a family, that's probably the reason that their milk consumption is going up, but we don't know that for sure. Okay, we haven't proven causality. But so the way we want to talk about this is that use terminology like as the number of kids in a family increases by 1, we see milk consumption go up by an average of 0.7 gallons per week. Okay, we don't want to say an additional kid causes milk consumption to go up by 0.7 gallons. We want to say things like it's associated with, okay? So because that's really all we've shown thus far, is that they tend to move together, and we can say things like as the number of kids goes up by 1, that's associated with an increased milk consumption of 0.7 gallons. Okay, so we'll have more chance to talk about that when we move to a new example. So let's, and by new I mean the one we talked about the other day. So I'm going to jump over to the correlation tab. We erase that. We talked about correlation, we talked about this example of ice cream sales and temperature, and how those two might be used or might be connected, right? We walked through calculating the correlation by hand again, and then we turn to regressing. Okay, so this was the idea of trying to regress temperature on our ice cream sales, with the idea that we might want to, just going to get rid of this temperature squared. We might want to better estimate how many ice cream cones we might sell on a given day, so that we could potentially, take the right amount of ice cream out, or make the right amount of cones, or closer to the right amount than just guessing the average. So again, without any type of regression, we might just guess every day we're going to sell somewhere near the average of 175 cones. But when we take this into account, we can hopefully get a better guess based on what the weather might be. So we had 20 days of data here where we knew the temperature and the sales. And so we can smush those together again, running a regression through data analysis. Okay, so we'll try to be nicer to my computer. Hopefully it won't freak out again. So, so I'm not going to rerun the regression. It spits out what we see here. Okay, and again, we can see that R and R squared. And jumping down to what we typically look at, again, we get our coefficients for what happens with temperature and the intercept. We can see the t-stats. Again, we don't really focus on that intercept that much. It is testing whether or not that's different than 0, but that doesn't tell us much. Okay, but this temperature does. And we see now we don't have just 4 observations, so we have a reasonable number of observations at 20, and we in fact can pick up that in this made-up data that we do tend to, we can reject the null hypothesis that there's no connection here. Okay, so we do tend to see higher sales when the temperature is higher. Okay, and so we can again, remember this is that sales hat. We're trying to predict how many sales of ice cream that we're going to have based on temperature. And so we can plug in those values. I'm going to zoom in a little bit. I realize this is pretty small. And we can fill out that equation. Again, what we would say is as temperature increases, so as we see an increase in temperature by 1 degree, it's associated with an increase of sales of 2.73 ice cream cones. Again, we're not saying it's causally linked. Again, we might have reason to think that it is, that's the driving force. But as we'll see in a few minutes, that's not always the case in a regression output. So let's do a similar thing. right? Because again, the whole point of this is maybe we can better predict how much we're going to sell. So we have, here I've just plugged in 82. So if it's 82 degrees, we think 191 sales. But down here, I've done the same thing. So I'm recreating that equation. Okay, and based on our coefficients here that we've produced in the Excel or in the regression. Okay, and so now I can play around with this, and if I do plug in 82, it should be that 191. And so if it's going to be 82 degrees tomorrow, a better guess would be 191 sales instead of the average of 175, right? So this added information can help us better predict what our sales might be. Okay, so if it's going to be 71, we think 161 might be a better guess. Now, let me just format that so I probably don't need all those decimals. Now, a couple things to bear in mind when we do regression, we want to make sure that we're not expanding beyond the scope of our data. Okay, so one thing we want to bear in mind is that this line that we're best fitting is really fit. I'm in the way of it, but it's really fit based on, just get over here a little bit, the data around it. Okay, so it doesn't make, and in fact, so even out at this end, we want to be a little cautious about making claims about how many ice cream cones we're going to sell when it's 110 degrees, because we don't have data out there, right? Our data in terms of temperature stretches from 61 to maybe 93. And so when we go beyond that data, it's referred to as extrapolating beyond our data. So I want to be cautious about that. And to highlight that, if we take this to kind of the extreme, what if it's 0 degrees? We actually get a negative value. Okay, and so I don't know if that means you're buying ice cream or it doesn't make a whole lot of sense. But clearly 0 degrees is very far from any of our data that we used to build this model. Okay, so and even if we 40 degrees, yes, it's a positive number, but that's very far from. It's a very different situation than the data that we used to build this model. So that's just kind of a word of caution that we want to make sure that when we use it to predict, we're predicting kind of within the bounds of our data. Okay, so next I want to turn to kind of what we're introduced to in chapter 14. And again, this is a very brief introduction, and as you can see in the assignment, really what I want you to do is just kind of be able to see a multiple variable regression and kind of wrap our heads around it. So on the multiple regression tab, what do we have going on here? So we actually have more information, right? So we won't be stuck only taking, let me get rid of this quick, only taking information about the temperature. Of course, we could keep track of other things. So for instance, and here's where I changed it from the last Friday's version. I have Doug's dogs written down here. Okay, and this is simply maybe every time you were out there, you made note of whether or not you took the temperature reading, but you also made note of whether Doug was next to you selling his hot dogs. Okay, you just wrote that down, and maybe that can help explain or help predict your sales. I also have weekend down here. We'll set that aside for now, but of course we could keep track of many more variables. So what we're going to do is a multiple regression. Okay, and we're going to use all of that information to try to better predict our sales. So this, let's see if this will pull up. Okay, good. So the way we do this is to expand our equation and say we still are interested in y hat, and it's equal to a plus, but this time we're gonna include b1 x1 plus b2 x2. Okay, and we could expand this further down and have x3, x4, x5, where each x is a new or a different variable. So in our case, x1 might be Doug's dogs, and x2 is going to be temp. Okay, and so we can take that extra information, and to put that in a context of what we've been working with, we're still doing a linear connection. We're just in this case, we're adding a third dimension. Okay, so my artistic skills here are going to fail us, but we could think about plotting this data in 3 dimensions. And actually, I just encourage you to look at the text because it's a better depiction than what I'm trying to do here. But each of these data points, so this data point that I've poorly drawn has the sales, right? So it's in 3 dimensions. So it has the number of sales, it has the temperature, and it has whether or not Doug was there that day. Okay, so it has 3 values associated with it. It's a single point in a 3-dimensional space. And as we expand to x3 and x4, it's still a single point in 4 or 5-dimensional space. We quickly lose the ability to even depict it on a 3-dimensional graph. But the concept remains the same, is that we can predict that value, right? So we can get a y hat and then measure how far we missed based on our prediction and what the actual value is. So the whole process remains the same, is that we can get a residual from our prediction compared to what the actual value was. Okay, so the whole process repeats itself. So the big change in our process is that we no longer do the correlation to B to A. We don't have that process, and in fact, Excel doesn't strictly do that even in the simple regression. So the way we do that is using what's called linear algebra. So if you're deep into math, it comes typically after maybe Calc 2 or Calc 3. There's a course, linear algebra. Some of you may have gotten there, some of you may sometime, many of you maybe never will, and that's fine. We're not gonna, you don't actually have to do this by hand. That's why we have computers. But it uses linear algebra or matrix algebra to do this. But the end result is that it's still finding the line that minimizes that sum of squared residuals. So we're still going to find a y hat. We're going to fit that line through 17-dimension space and measure the distance for the residual. We can still test individual betas or b's, right, to know whether or not they're different from 0, right? So we're going to get a t-test for each value, for each coefficient, okay? And we see that in the regression output. So let's just take a glance at this. Again, this is, so let me click through to do the regression. This time, so we need to pick our y. We're still trying to predict ice cream sales. For the x's, in Excel, we do need to grab x's that are next to each other. Okay, a little different. In different programs, this isn't a requirement, but in Excel, you do need them to be connected or next to each other. So sometimes you need to kind of drag and drop and manipulate your data to get it as such. And we don't always have to have residuals on, but if I clicked OK, it would spit it out here, but without the highlighting, so I'm going to just cancel that. And we would get as follows. Let me get this out of the way. Again, we get an R squared, which tells us basically how well we've predicted the y. And one way to interpret this, I don't know if I repeated this earlier, but it's really picking up the percent of variation in y that's explained by the variation in the x's. Okay, and this time we have multiple x's. So how well do those x's do at explaining the variation in y? And here we would say the R squared is 57.57 or 57%. But let's zoom down to what are we getting from coefficients. Again, we get an intercept, we get that A, but this time we get two B's. Okay, we get B1 and B2. I guess, okay, I don't love this. I guess I reverse those. It doesn't really matter. So I've written out the equation where temp is x1 and Doug's dogs is x2. It's a little confusing because they're coming first and second reversed, but we can plug that in and say the coefficient, whichever order you have it in, the coefficient on temp is 2.19 and 19.854 on Doug's dogs. Now, one thing to point out is this 2.19. It's pretty close, but it's different than what we found in our 1x regression, okay? We found 2.73. So this is also one of the reasons why we want to be careful with causal language, is that this changes depending on what other x's are involved, okay? And this is always typically going to be the case is when you add in other explanatory variables, other variables to try to tell the story of your sales, of your y variable, the relationship between the x's and the y is going to change. Okay, so here we said as temp increased by 1 degree, we saw an increase in sales of on average of 2.73. Here, in the multiple regression, as temp increased by 1 degree, that was associated with an increase on average of 2.19 sales, holding all else equal. Okay, so that's changed. And also note that I said holding all else equal. So we're going to have a lot of moving parts, or a lot of possible moving parts when we have multiple x's. Okay, we could add in the weekend variable that we had. We're going to have multiple things moving. And so when we interpret one of these variables, we're only really talking about what if we move just that variable. We hold Doug's dogs equal, we change the temp. Or we change Doug's dogs, we hold the temp equal. Okay, so when we interpret a coefficient, it's always holding all the other variables equal. Another thing to note is that we are using Doug's dogs, which is a dummy variable. So rewinding back a month or two, remember we talked about dummy variables and we made some of those in Excel. 1 and 0, turned on or turned off. So here we see that in action. And so the way we would interpret that again is when Doug's out there selling his hot dogs, that's associated with an increase of sales of almost 20 ice cream cones. Again, holding the temperature equal. Now, the reason I've changed it from what it said the other day, I think I had it say home games, is to highlight that we're not making a causal statement. So we're not saying that Doug's dogs being present increases our ice cream sales. We're saying when Doug's dogs is present, we tend to see higher ice cream sales. And it would probably be a hard case to make that's a causal link, right? Doug showing up to sell probably isn't what, oops, zoomed in there. So Doug being there probably doesn't cause increase in sales. Okay, that would be hard to justify. Maybe Doug's dogs are so good that everybody flocks to Doug's dogs and then has dessert for us. So it could be possible, but more likely is something else is driving both of these. Okay, and what I had written down on the previous version of this is something like there's a home game. Okay, so maybe Doug only shows up to sell when there's a home Twins game. Again, non-pandemic time when people go to games. So this might be a case where there's a variable happening in the background where that's actually causing both of these, and there's not a relationship. There's not a causal link between Doug and our sales. There may be a causal link between there being a home game and our sales, but we don't have that data. So that's one reason to say we need to make sure that even though we see, actually in this case we don't have quite a, we didn't reject the null, but even if we had, we wouldn't want to say that this is necessarily causal, and we don't want to say necessarily that it's causal that the temperature, when the temp changes, that we increase sales. But if we're using this just to predict, we don't actually care if it's causal. Okay, if we can know whether Doug is going to show up, that's all we need to know. So we could call up Doug in the morning and say, hey, are you going to be out there selling your hot dogs? And he says, stop calling me, just check the home game schedule. And we say, no, we just want to know if you're going to be selling. And he says, yes, I'm gonna. And we can plug that into our prediction. Okay, so we, strictly speaking, if we're able to predict, he says, yes, I am going to be there. Okay, I know it's 79 degrees. I'll predict 191 sales. Okay, so as long as you can trust Doug that he's not going to get annoyed and lie to you, then we can use that information, and it doesn't need to be causal. Okay, there's a whole nother branch of regression, or regression is used to try to get at causal relationships, because those are important as well. But we also use it for prediction in these types of situations. So again, I don't know if we looked at this yet, but I built that same, right? We can build that same prediction system based on these coefficients up here, where it's, A, which is the intercept, plus the intercept on Doug's dogs times the number of Doug's dogs, and which is either 1 or 0, right? It's a dummy variable. And then plus the coefficient, that 2.191, times the temperature. And so we can plug in that temperature, again, thinking, how would we use this? Well, tomorrow we know it's going to be 83 degrees, and we know that there's not a home game. Sorry, we know Doug's not going to show up. We don't know if there's a home game, but we know that Doug's not going to show up. And so we predict 180 ice cream sales. And that, again, the whole point of this was maybe that's a better guess, or we hope that's a better guess than simply guessing our average of whatever it was, 175. Okay, so we'll end here soon. What do I want you to take from this? Again, we're not going to be masters in this week and a half. I want you to understand what the goals of regression are. What it loosely shows, right? So it's showing a linear relationship. We're trying to describe the relationship between these variables linearly. Okay. One other thing that I failed to mention. This multiple regression or regression is flexible in that it is going to depict a linear relationship, but it does not restrict us to only linear variables. Okay, so we can put things in like temperature squared. Okay, probably not useful in this case, but we could do that. Where would we do that? Well, again, thinking back to that happiness and age, where we saw the curve and it's actually age squared, or age squared does a better job depicting it. I don't know if we said that specifically, but that arc, right? Think back to your early math. A parabola like that is x squared. When we run regressions about happiness, we actually include age squared as one of the variables. Okay, so we can put in nonlinear x's. It's just the relationship is strictly speaking linear. So we can do things like, temperature squared. We can do interactions. So as you're thumbing through chapter 14, you'll see a little discussion of this. We could do interactions. So we could do Doug's dogs times weekend. Okay, so that's where that's only going to be turned on when it's both Doug's showing up and it's a weekend. Okay, so we won't get into the nitty gritty of all of that, but just know that those are available. Other things that are typically done, you could take the log of a variable, where we moved more towards a percentage interpretation. Okay, so there's a lot of deviations we can make from this, and some of that is based on what type of variables we put in. Yeah, so it's flexible. I don't expect you to kind of grasp all of that. So what I do expect is that you kind of understand the overarching goal, that we're explaining this linear relationship, how it connects to correlation, right? So I expect you to be able to calculate correlation, right? You're going to have some practice with that, and calculate from the simple version of just one x variable. We can calculate that correlation, calculate B, calculate A, to be able to produce that equation. And understanding that we can calculate and run a t-test, right? So we can see the results of it here, but understanding that that's running those t-tests that we've done time after time in this class. So yeah. And then a little bit of that understanding of how to interpret the variables. So what it means to increase one of the variables by a unit, and that's associated with an increase in the y variable. So as you study, obviously we have an exam coming up in a few weeks. The assignment will do a good job of kind of depicting what I'm hoping you can grab from that. The other thing, I don't know if I mentioned this yet. I think I might have at the start, but I will have office hours for the next couple weeks, and I'll probably add in another day as we go. But yeah, so please make use of that. Again, if you want to talk about what we're studying here, or if now as we've finished up the semester, if you have thoughts or questions in general about statistics, please feel free to jump on and we can chat about those now that we've kind of covered the gambit of our statistical beginnings here. So I think we'll leave it there. I'm sure there's something I'm forgetting, but I'll make sure to email you if there's something specific. So we'll leave it there, and I'll also stay on for a couple minutes if people have questions now. But other than that, we'll talk to you soon.